Today we will learn about the hardware components of a computer, and also start doing some practice on the command line. So the main hardware components in a computer, what you see here is a motherboard, which is actually there for holding all the parts together. The CPU, which is the brain of a computer. Memory, keeping data ready for the CPU. A storage device to store all your data and results. The power supply, just giving the power to the computer, and different kind of extensions and peripherals. But for us, what we have to know more if we do bioinformatics is actually only the three main components: the CPU, memory, and storage device. I left the graphics card and network gray, a bit darker gray, because some of the bioinformatics software can use new graphics cards. The graphics cards nowadays have a lot of computing cores, which can be used by certain applications in bioinformatics. And also the network is important, because if you are running something, or you are planning to run a bioinformatics software on multiple computers, multiple computing nodes in a HPC cluster, you have to know that they are communicating with each other through the network, which will be always much slower than anything inside the computer. So let's start with the CPU, which is the central processing unit. That's actually the thinking part of the computer that does all the calculations. And of course, every software and application uses the CPU, but not with the same intensity. What you have to know as when you do bioinformatics about the CPU, but the CPU of that computer you are working on, is actually the speed, the type, and the architecture. The speed is nowadays is measured in gigahertz. The type can be like a desktop CPU or laptop CPU, or actually a server CPU. They are basically different in power consumption, in speed, and also in reliability. Server CPUs, while they are the most expensive, of course, they are the most reliable CPUs. And the architecture is also important, because sometimes there are programs or applications that are only compiled or written to one specific type of architecture. Luckily, you are mostly working on a 64-bit or an x86 architecture, so you don't have to be very careful about the architecture. But if you know that your server or your computer is a bit weird, it's not a usual computer, then you have to know what is the CPU architecture. CPUs can have multiple cores, and each core can have multiple threads. So there are cores that are single-threaded, and there are cores that are multi-threaded or has dual threads. What does this mean? The cores actually are separate, independent small CPUs inside the CPU. So if you know that your computer has 4 cores, then you can be sure that 4 CPU cores can work independently from each other, and can work in parallel with each other without any problems, without any slowdown. While if you have multiple threads, so for example you have 4 cores, but all of them have 2 threads, that means that you actually have 8 computing threads, but it's not 8 real computing threads, it's only 4, but all of them are able to can handle 2 different threads at the same time. Most of the bioinformatics software that can run on multiple CPUs or multiple cores are running on separate cores and not really happy to run on separate threads. So even if you think that you have 8 separate CPUs or separate cores, they are probably just virtual. So you have to know how many cores you have, and you have to adjust your bioinformatics software to the number of cores and not the number of threads. So we are already speaking about parallelization. So if you run a program in multiple cores, that means that you are running it in parallel. In theory, if you run something on 2 cores, then your speed will be the half as you run something on a single core. In a few cases, this is true. If your computation is extremely dependent on calculations and on the CPU, then it can scale very well. But mostly in practice, it much more looks like something that you can see on the diagram on the upper right corner, that with the number of CPUs you are using, the speed is not going up linearly, but there is a kind of slowdown. This slowdown can be caused by many factors. If they have to access to the storage device, then the storage device speed can be limitation. If they have to access the memory, then the memory amount, the memory speed can be a limitation, or they have to share something. But most of the time, they are just simply waiting for each other. So if you give a chunk of work for each course, then there is a point where they have to, when they finish their work, and they are waiting for each other, and then they will be served with the data again. So many times the cores or CPUs just waiting for each other to finish with their chunk of work. The most CPU-hungry applications in bioinformatics are modeling, even if it's like molecular modeling, folding of a protein, or mathematical modeling. These are very CPU-hungry applications. De novo assembly, when the assembly has to combine billions of reads or billions of short sequences. Multiple sequence alignment is very CPU-hungry, and also the phylogenetic tree reconstruction, when the program has to go through a lot of data and do a lot of calculations. So the next component you have to know about is the memory in the computer. So the memory is there for temporary information storage during the application run. This is very important. It's just temporary. So what is in the memory will be purged, will be deleted from the memory as soon as the application stops running, or as soon as you turn off your computer. So it's very important to write out your results before the application stops running. Memory is again always used, but with very different intensity by different programs. The parameters you have to know when you check your memory is, of course, the amount, and again the speed and the types are important. The amount is usually measured in gigabytes, and I will speak what is the average amount of memory you should have in different kind of computers a bit later. But also the speed again is measured in megahertz or gigahertz, and again types can be different. So for example, the laptops have low power memories just to be able to work more from a battery, but that means that they are slower. When the computer is running out of the physical memory, it can use an emergency memory, which is actually a small piece of space on your storage device. But you have to know that this is only for emergency, so the computer cannot really work from or use the storage device as a real memory. It's way much slower. So as soon as the computer starts using the emergency memory, it will slow down significantly. That's one of the main reasons why computers slow down. Of course, when you are making your own script, you should learn how to avoid using too much memory. So, for example, if you are parsing a FASTA file or a FASTQ file, you don't really have to read in the whole file in your memory. If you just do, for example, a QC and you want to throw out the low quality reads from a FASTQ file, you just have to check 4 lines, the sequence, not even the sequence, just the you just have to put these 4 lines, the first 4 lines into the memory, check the quality score, and if it's good enough, then write it out to another file and delete the data from the memory and read in the next 4 lines to the memory and do the same. So in the program will only use that much of memory which is needed for storing 4 lines, which is almost nothing. Parallel processing is again very important, because if you are doing some kind of calculations on the data which is in the memory, then the programs can choose from 2 different approaches. One approach is they allocate different data or different parts of the memory for different cores. So that's what I told before, that a chunk of data will go to core 1, and a chunk to core 2, and core 3, and core 4, and so on. And then they have to wait for each other, and then they can work on the other core's data and do their calculations on that. So in this case, because they are sharing the data, they are sharing the memory, they don't slow down each other by accessing the memory, but they have to wait until each of the processes finish. The other approach is to multiply the data in the memory and provide a full data set, the full amount of data for all of the cores. In this case, they don't have to wait for each other, but the problem is that you have to have that amount of memory you want to use. So if you have 2 gigabytes of data in your memory, but you want to use this approach on 4 cores, then you will need 8 gigabytes of free space, because all cores will have that 2 gigabytes of data. The most memory hungry or sensitive applications are again the sequence realignments. It's especially sensitive to the speed of the memory. Of course, all the sequence searches when you have the database usually in the memory, so BLAST, PFM. The Novo assembly is very sensitive to the amount of memory. You have to have a lot. And of course, if you have large distance matrices, they also have to be in the memory. So the last part of the computer you have to know more than just hearing about it. So you have to know what is inside your computer is the storage device. And the storage device is there for permanent information storage. So you have your raw data, your results, everything in your hard drives. Of course, it is used during, again, almost all applications, but again, very differently. If you are doing molecular dynamics simulations, you just have to provide that few kilobytes of data, which is a PDB file, to start the run. But if you are doing a whole genome alignment, then the storage device has to provide the whole genome to read in to the memory first. So of course that makes a big difference. And again, the main differences in different storage devices or the main parameters you have to be sure what you have is the speed, reliability, and of course size. So on the right hand side you can see a few different types of storage devices with the conventional hard drive with spinning disks and magnetic storage on the top, and then 2 different kinds of SSDs, solid state drives, with a SATA interface and a connector which can be directly put on the main board. And the last one, of course, is a flash drive. The speed at the moment, the highest speed you can get is from the two middle SSD disks, especially if you are reading in multiple files. They are way much faster than the hard drive. The hard drive can be very fast if you are reading in one big file, and especially if that one big file is in one piece on your magnetic disks. And of course, the flash drive is very good for transferring data. So in the previous slide, I spoke about the emergency memory. So when the memory is extended with a small piece from the storage device, but you can also do the opposite thing. So if you have a lot of memory and you need a very fast storage device, you can allocate memory to behave like a storage device. In a few cases, the programs will be way much faster this way. Of course, there is a drawback. As soon as the computer turns off, or the RAM drive program turns off, you will lose everything on that storage device. So you have to be very careful with this. But you can use this kind of trick to increase the speed of applications sometimes. You should know the word RAID. Sometimes the RAID is usually not in your personal computer, but in many cases it's in servers, or especially HPC servers. So the RAID can be different, but usually the two main types are when you have two similar storage devices and you are mirroring one to the other, which makes your data safety much higher. So if one of the drives fail, then you will have the complete copy of your data on the other drive. This will increase the safety of your data significantly. The other usual RAID configuration is when you are merging two hard drives and merging their storage space. So if you have 1 terabyte to 1 terabyte SSDs, you can make a 2 terabyte storage from those two. It will increase the speed, but it won't do anything with the data safety, of course. And there are many different combinations of these two. Parallel processing is again very important from the storage device point of view as well. If multiple cores have to work on data which is on the storage device, they have to read in at the same time the data from the storage device, so they can slow down just because they are waiting for each other to read in or to access the data on the storage device. You will very soon meet with data compression in storage devices. So if you need to save some space, you can use different compression algorithms which will package the data. You won't be able to use the data, but you can store the data for a long time. Of course, you can uncompress them and then you can use them. But the main reason why you should use data compression is just to save space and compress your raw data and backup. So in terms of storage device hungry applications, of course your raw data is usually using a lot of storage data, but also if you are doing big data processing or production, you have to know how much extra space you will need at the end of your pipeline of your application run. So on the following slide I will compare the three main working environments you will meet when you are doing bioinformatics. So the first column is of course your own computer, working computer, which can be a desktop or mostly nowadays it's a laptop. The second one is an in-house server like we have in our Hammond building, which is usually a bit more powerful than your desktop. And the third one is a high-performance cluster, which is a centrally administered computer with a lot of computational power and very reliable computer parts. So in terms of what you can do on your computer, of course on your desktop or laptop you can do everything because you are usually the admin. You have admin rights, you can install anything, you can compile anything, and you can ruin your desktop or laptop easily with those things you are installing on. But at least you are free to do anything. On the in-house server you probably know the admin, so you can ask the admin to install those applications or those programs that requires administrator rights. And on the HPC cluster you only have very limited user rights. You can ask things, for example at the Cambridge University you can ask installations, or you can ask new models from the HPC admins, but it's usually not as simple as just go to meet with your in-house server admin. In terms of running your scripts or programs or applications, of course on your desktop or laptop there's no waiting time. If you want to run something, just run something on your computer. On the in-house server, and most of the time you have the resources available on the in-house server, but you have to know that you have to sometimes share your resources, share the storage space. If you have multiple cores, maybe someone is running on 4 cores, so you only have 4 left. You have to check these things, you have to organize your runs, especially if you are doing something long with other people who are using the in-house server. The high-performance cluster from this perspective is very different. You never start a run immediately on an HPC. You are submitting your runs to a queue system, and it depends on your priorities. So if you are using free CPU hours, you have low priority. If you are paying for the CPU hours, you have a higher priority. And depending on many other factors like how many CPU you want to use, how many hours your run is planned to go, these things are influencing your place in the queue system. In terms of those components we were speaking about, CPU, memory, and storage device, the laptops, desktops are usually 4-core, has a 4-core CPUs, and many times they are multi-threaded. So sometimes you can see that there are no 8 CPUs in my computer, but it's actually only 4. But all 4 are hyper-threaded. So you have to know how many real physical cores you have. And in terms of memory, the average memory in desktops, laptops nowadays is 8 to 16 gigabytes of RAM. In an in-house server, you usually have at least 2 or 4 times more CPU cores. Sometimes they are multi-threaded, but not always, so it's very important to check the number of physical cores. And on average you have 64 to 128 gigabytes of RAM memory. On an HPC, you usually only have physical cores, so the number of CPU cores you see is really the number of CPU cores, not hyper-threaded, and it can go up to 64 or even more CPU cores nowadays. And the memory is usually 6 gigabytes per CPU cores or 12 gigabytes per CPU cores, but can go up to 1.5 terabytes nowadays easily. In terms of what type of components you have in your computer, desktops, and especially laptops. They have low power CPUs, low power memory modules, which means that it's not just the power low, but also the speed is lower. In the in-house servers, you usually have very high power and high speed parts. So in comparing the three, from this perspective, probably the in-house server is the fastest per CPU core, faster than the HPC, because in the HPC you usually have a long life, high reliability parts. They are also high power, but they are sacrificing a bit of speed in exchange to long life and high reliability. In terms of storage, on a desktop or laptop, you usually have a single internal storage. Very, very insecure. If you are keeping your results in a cloud, that's very secure, but you usually cannot really keep your raw data in a cloud, because raw data is usually a lot. So you have to be sure that if you have your raw data on your laptop, then you have at least one backup from it. On the in-house server, you usually have high-speed internal storages, and in many cases there is an NAS, a network associated storage, attached to in-house servers, which means that you have a higher data security on these systems, and higher data speed as well. That doesn't mean that you don't have to have a backup copy. On the HPC, it's usually a very sophisticated professional storage system, but you don't really have to worry about that. The only thing you have to worry about on HPC is your quota, the amount of storage space you are paying for, because if you run out of your allocated space, then you will lose all the subsequent results, because they just simply won't be written to the storage device. The typical tasks or programs you are running on these three different environments. On your desktop or laptop, you usually run your short few minutes or few hours tasks. On an in-house server, you can run hours or even few days tasks. And on a high performance cluster, you are usually running few hours or maybe up to 1.5, 2 days long tasks. The reason why you shouldn't run very long tasks on HPC, because as soon as you are requiring many cores for many days, you will go to the very end of the queue system, and your run will start very late. So it's much better to fragment your tasks to short runs and make a script to run them after each other. So usually you can run the longest ones on an in-house server. The most typical way how you work in bioinformatics is that you are developing your methods and your applications and your scripts on your own computer, usually on a small toy dataset. You are optimizing your runs and steps after that on the in-house server on a few samples, and as soon as you have the optimized pipeline, you are going on the HPC and run on the full dataset. The reason why you don't want to optimize your runs on the HPC, because if you are using free CPU hours, then the whole optimization will take too much time, because you have to wait until your runs will be executed in the queue. Or if you pay and you will have higher priority, then you are paying for the optimization, which is not really worth it. you are paying for this usually the same run, because you are just changing one or two parameters on in your run. So run pipeline when it's ready. And finally, the operating systems on these environments. On your desktop or laptop, it's usually Windows or Mac. Sometimes it's Linux. On the in-house server, it's much more Linux, sometimes Mac OS. And on the HPC, it's almost always Linux. Okay, that was the last slide. And now we'll open the terminal and learn a few very useful comments, and also try to find out how we can learn more about the hardware of the computer you are working on by using terminal commands. I will put it here. So here you can see that I have the console, which you can access on your Mac by going into your other and choosing the terminal app here. If you have Windows, then you probably already installed the virtual machine and the virtual Linux on it. If not, it's okay. It's not a big problem. You can just follow what I'm doing, but it's much better if you are doing the same what I do. So it's usually much better. So at the moment I have 3 terminals. All of them are my own Mac. So but the first one remain my Mac. The second one will be a Linux, which is my Raspberry Pi. And the third one will be the HPC. So I can show you the differences you will see on each. Okay, so it's interesting. It's working. So the first thing, there are a few commands you can use to find out what kind of computer you have. So on the Mac, there is a program called System Profiler, but you have to use it with detail level mini. Otherwise, you will have a lot of things on your screen. Even with this one, you will have a lot of things on your screen. So it will give you a lot of things about the hardware you have. And this is already a very good time to see how we can look back, or how we can find important things in this huge amount of data. You can, on a Mac, you can just simply use a scroll and go back and check, oh, where is my CPU? Where is my CPU? But it's much easier to filter this output. So what I did actually here, I don't know if you can see the bottom of my terminal. I will just pull it up a little bit. So what I did is I executed this program with this option, the detail level, or this flag. And within the detail level, the option is mini. I will just mute my phone, sorry. If you do this, the program will run and will put the results on your standard output. Your default standard output is your terminal screen. It's also called sometimes STD out, or just simply standard output. You can do multiple things with the standard output. For example, you can put it into a file. So what I did before, okay, let me just show you. Okay, so I'm in a folder now, which is completely empty. Okay, I will show you what I did a bit later. So I again run the same program I ran before, but I put this arrow-like thing after that and say that I want to put this into the system data.txt. Okay. So again, there are a few things which will come up here because this is now going into my standard error. When I'm using this sign, everything which went to the standard output was put into the file. This is a very useful thing, and you will use this many, many, many times. This is how easy to put anything which went to the standard output into a file. You can also put your standard error into the same file or into a different file, but it's not extremely important at the moment. So if I'm saying ls, which is the second thing we have to learn today, which is listing the content of your folder where you are, and I can see that there is a new file there, and I can look into it. But before looking into it, let's see how this file looks like. So the ls, again, it's a program. It is somewhere it's a small application which is on my computer as well, which I can use to list the files. But I can also use ls in a different way. I can say ls -l, which means that it's the same kind of list of my folder, but with a much more data, much more detail. If I'm doing this on the Raspberry Pi, it is the same ls -l. If I'm doing it on the HPC, it is again the same. So the ls is a completely universal command line command, which is working everywhere in any kind of Unix or Linux-based environment. It's sometimes colored, sometimes not. Here it is colored. You can make colors on Mac as well, but it's not the most important thing. Let's see what we have here. This string in the beginning is a very, very important string, and I will speak about this in a moment. This one actually is, it's just the number of, I think, files you have. So if you have a folder, like here I have folders, the blue ones, and I think I can see the number of items within the folder, but it's not important. This is very important. The next thing is the user who owns the file. The next thing is probably the group ID here, which is a bit strange on my Mac. It's much nicer here on the Raspberry Pi. So this is the user, and it has its own group. And then the size. The folders are usually have the same size. They don't really have size. This is not the content of the folder. This is just the size of that thing on your storage device, which says that it's a folder and its name. So it's not the size of the folder. There are different. There is a special comment for looking into folder sizes, or how many files or what size of files you have there. Here again, you can see a bit more here. For example, these light blue things, which are links, but I don't go into the details of those ones at the moment. And then you have the size here, which is in bytes. If you say ls -lh, then the age usually for most of the programs means that it's a human readable format. So you can see now that it's a 80 kilobyte sized program. And then you see when it was created and what is the file name. Okay, so let's go back to the beginning. This is a string which is divided to 4 parts. The first part is the very first thing here, which is nothing, or just a dash, because it's a file. As soon as you have a folder, you have a D there because it's a directory. Okay, so that's the only thing why the first thing you have. If you have a link, you will have an L. It's not very important because you know that you are looking at a folder or a file anyway, for example, from the colors. The next three things are exactly the same length, 3 characters in the beginning, 3 characters in the middle, and 3 characters at the end. The R's means that this file is readable. And this is where we're going into the Unix file system strength, the permission system. When you are working on your Mac or Windows and you are saving your files, of course, you can access your files later on. If you are saving anything to a flash drive, anyone can access to those files as soon as they are plugging that flash drive into a Windows or a Mac. In a Linux file system, you can restrict the access of files in 3 different ways. You can restrict your own access. So if you are the creator, you are the owner of that file, you can restrict if you are allowed to read, to write, so modify the file or execute the file. I will show you why the execution is important a bit later. You can also restrict what your group can do. So for example, if you are working in an in-house server environment and you want to share your data, but you don't really want to share your data with everyone, then you can create a group with your teammate, and you can allow read and write access to that group only. You can change the group, of course, of the file. And the last 3 things, which again should be R, W, and X here, is the access restriction for everyone else. So the first 3 is for the owner or the user of the file. The next 3 is for the group. And the last 3 is for everyone else. These things can be changed very easily. So if I say CEH mode, which is how we can change the restrictions or the access for a file, and I would like to say, for example, U minus W. Yes, there is a question. Maybe I should have this open here. Okay. See you next time. And then I will write in the file name. And I used a magic button here. I will tell you again as well. And I say ls-l again. Then you see that W just disappeared from here. What I said is that I want to change the accessibility of the user, and I want to subtract, I want to take away the writing accession, so I won't be able to write this file anymore. And of course, I have to tell what is the file name I want to change. And in the same way, I can just add this back to the file, and it's now looking the same as before. I can also do it for the group. So if I say G here, which is for group, then as you can see now, the W is there. So all my group mates, which on this Mac, which is my own Mac, there are of course no other users here, but it would be now read and writable as well, not just, sorry, read only. And I can do the same thing for everyone else, which is not 0, but O as others. And now everyone has an RW. As soon as you will start writing your own scripts and you want to execute those scripts, you have to make them executable. You can make any file executable, but of course it doesn't mean that you can execute them. So I can make this system data txt executable, and I can try to execute it, but it will just give me an error because it's not an it's not a program, it's just a text file. But I can do it, so I can say that I want to change the user rights and give the executable flag, which is X. And now, as you can see, the X appeared there as well. This is again very important if you write a script and you want to allow other people to use that script. For example, if you are working again in an in-house server environment and you want to share your fantastic bioinformatics program with someone else, then you have to put this X flag here or here. It depends on if that other person is in your group or it's just a random other person. There is a very easy way to set these kind of user rights very quickly. So just imagine that the R worth 4 points, the W worth 2 points, and the X worth 1 point. So if I'm saying chmod 700, that means that for the first third, this one, I want 7, which is 4 plus 2 plus 1. So R plus W plus X. But for all the others, I don't want anything, and that's why it is 0. And I'm doing it with the system data txt, so it will look like this. So nothing for the second and the third part, but all the rights for myself. If you are making your scripts and at the point when you have 10 or 15 new scripts and you want to make them accessible to someone else, you can do this very fast by just simply changing all your script permissions in one step. And let's say you want to keep the read and write accession and of course the executable accession for yourself, but you want to let other people read your file, not write, because you don't want them to modify your script, but you want to allow them to execute your script. So your first number will be 7, like this, because it's 4 plus 2 plus 1. But for the others, you only want R and X. R is 4, X is 1. So it will be 755. Let's try 755. And you will have that kind of permission pattern, what is very typical if you are sharing your script with other people, but you don't want them to modify your script. I think it would be a nice time now to try it on your computer if you haven't tried yet. If you don't have any files, any folders yet, let's do it here on the Linux. You can make your toy directory, sorry, with the make directory command, mkdir, and then you are writing the directory name, which can be temp. If you have a temp directory already, try not to overwrite it, but usually you don't have, just check it with ls. And now I have the temp directory here. You can go in to your temp directory with cd change directory. Probably you already know this because it was in that video I asked everyone to watch before coming into this course, this meeting. So we have the temp directory, which is completely empty. If we check it, yes. And if you just want to have a file, what you can try your permissions set or modify. just simply use the touch command. Touch command will create a file, and let's say that it's a new file. You don't have to use extensions. If you want, you can use txt, but you don't have to. And then if you say ls, the new file is there. If you say ls-l, you can see the whole permission and data. And you can see a 0 here because it's a 0-sized file. There is nothing in that file. It's just created, but there's nothing inside. So finding out who you are is also an important question. For example, if you want to share something with your own group only, there is a command w. No, this is not the ID. Sorry. If you say ID, this is again, I think, working on any kind of environment, here, here, and here as well, then you will see that your user ID is this, and this is your username, and your group ID is this one. But also on the HPC, for example, I'm involved in my own group. I'm involved in the RDS, and the group which is called RDS, and also our group, which is our working group, actually. There on the Raspberry, there are so many groups that I'm involved because I logged in with the Pi user, which is the basic user. What is happening if someone wants to look into a file on a Mac? I just found out today that the server or the operating system configuration files are not in the etc folder. I will speak about folders a bit later as well. Maybe not today. But let me just show you something. If I want to say less is a command which you can use if you want to look into files. That's a very useful command if you want to, for example, if I want to look into this system data txt, then this is it contains, and with pushing Q, I can kill it. I will go back to the console. You will use less a lot of times. So if I want to look into a file which is a bit more restricted, there is this file, the sudo-rs file here. As you can see, the user is the root on the Unix or Linux Pi systems, but also on the Mac. Root is the super admin. So root can do everything. That's the super user. And as you see, this file is a read-only file and only for the root. And it actually contains all those identifiers who are allowed to do super user things. So if I'm as just a simple user, try to look into this file, then it will tell me that it's and the permission is denied. It's the same with any kind of Linux system. So you can very easily protect your files, protect your scripts on a Linux file system. Going back here, and I think I will tell you only a few other comments now because I think it was quite a lot. But you can always, of course, Google, how can I find out what is the CPU number in my computer? What is the memory? But I think there are some very basic commands you should know about. For the memory, you can just use free. Not on a Mac. I will have to find out what's the command on Mac. But on a Linux file system, you can use free. I think there should be a -h. Yes, again, -h means that it's a human readable format. So this is my Raspberry Pi, which has 4 gigabytes of memory, from which 204 is used and 3.3 gigabytes is free. If I'm doing the same thing on the HPC, then the HPC, this login node has 187 gigabytes of memory, a lot. And actually quite a lot of them is used. If you want to try to find out what is used, and again, this will be one of your most, right, is there, most often used commands is the top. If you say top, you will see what is running on the server. Okay, it's again real time. It refreshes, I think, every 1 or 2 seconds. I can say the same on my Raspberry Pi. There is nothing running on Raspberry at the moment. And I can also say the top on a Mac. It's not really nice on Mac. It looks much worse on a Mac. But you can see that, for example, my Zoom is running and using 100% of CPU. Luckily, I have 4 CPU cores in this laptop, so this is only 1 core, actually. My total CPU amount is 400 or 800. I'm not sure about how the Mac is calculating this. But also, if you look at here, the reason why something is running at the moment on this login node, this is some kind of maintenance program which is executed by the super user again. On Linux file systems, not on Mac, if you push 1 in top, then you can see how many CPUs you have in that computer. In this one, we have 32, numbered from 0 to 31. By pushing 1 again, you can just collapse this. The same thing on my Raspberry Pi. If I save 1, it turns out that this small credit card size PC has 4 CPU cores, and actually these 4 CPU cores are physical CPU cores. But if I want to find out the speed, then you can use the ls-cpu command. So it turns out that it has 4 cores, as you can see here. There are no virtual cores, no hyperthreading, but the clock time, or the clock speed, or the speed of the CPU is only 600 megahertz, which is, or the top is 1500 megahertz, which is very slow. The stop top is the same as less, just push Q. Press Q, yes. I don't know if we have ls-cpu here. I'm not sure that I'm allowed. Yes, I'm allowed. So this is the HPC. So if you look at the HPC configuration, the CPU number is 32. In one CPU, there are 16 cores, but actually these computers have 2 physical CPUs on the motherboard. So this is why you have in one, 2 here at the sockets. And the speed is here, so it's 2600 megahertz. On the Mac, if you want to find out, again, I press Q. If you want to find out what kind of CPUs you have, then it is working with that kind of system profiler command I used long before. But luckily, I don't have to remember because I have the history. The history is saving your last comments, your last 100, 500, or 1000 comments, depending on how the server is configured or your computer is configured. And you can access these comments by pushing the up arrow, or so I can just go up and up and up and finding this system profiler minus detail level mini, which I pushed or put the output into the system.txt. If you want to find something which happened days or maybe months ago, but you think that it's not too far in the past, so it should be within this 1000 last comments, then you can open that file actually. You can go to your home directory by saying cd. If you say cd anywhere you are on a computer, so let's go. Let me just go to a very different directory. Okay, I'm somewhere completely far away from my home directory. If I say cd, I'm back. What is my home directory? pwd. Again, this was in the video, I think. My home directory is /home/pi. And I think I will speak about the whole structure of the file system next time, because it's too much for today. I think the last thing I will tell you is how you can go back and see your comments. So there is a file called bash history. Again, I'm using less, which is the program you can use to look into text-based files. This file is a hidden file. So if I say ls here, it's not here. Even if I'm say ls minus l, it's not here. But if I'm writing ls minus la, and the a flag means that I want to see hidden files as well, then you will see much more files with dots, starting with dots, and these are all hidden files. And as you can see, the bash history, which is my own history, again, as you can see, because of privacy, it is only readable and writable to me, to nobody else. Okay, so again, this is well protected in default. And if I want to look into, I say less.bash underline history, and here I don't type more, and this is the magic what you can also use, and you have to use, and you will use a lot on console. Just press tab, and tab will auto complete your command. And if you look into, you can see that in many lines, this is what I did on my Raspberry Pi in the last few months. Okay, and here you can scroll and search, or you can search directly by pressing the slash, the normal slash, and say that, for example, I'm looking for the word dev, and it will be there, for example, when I installed a few libraries, a few programs to this Raspberry Pi. Again, you can go out from less by pushing the Q. And there is only one more thing I really want to tell you today, and we will go through this again, I think, on Thursday, because I think, a bit too quick, is grep. How can I find out from this file, this system data file, what is my CPU number? The easiest way is using grep. Grep is a program that can find a line in your text file which is matching the thing what you are looking for. So let's say that I'm looking for CPU, this word CPU, in the system data.txt. And if it finds any line with the word CPU, it will put it to the standard output, so to the terminal for me. There is nothing. The reason why there is nothing, I know that there is at least one line with the word CPU, but, and this is again a very, very important thing in command line is always case sensitive. So maybe that word is starting with a capital C and then PU, or capital C, capital P, capital U. I don't really know. But luckily, I can use the grep minus E, which means that the grep will be case insensitive. Not the Linux, but the grep will be case insensitive. Oh, and there is no CPU. I thought there is, but then look at processor. Okay, it was processor. But again, we just simply looking for the word processor. There is nothing because it is starting with a capital P. Okay, so that's why we always have to be careful with case as well. And there is only one processor in my laptop, but if I look for cores, then I will find out that the total number of cores is 4. But if you check with some kind of graphical user interface program, you will see that, oh, there is 8 cores in this laptop. Even if you buy this laptop, it will be advertised on the Apple website that it's an 8-core, or it has 8 cores because it has 4 physical cores, but each cores are hyper-threaded. So theoretically it can work as a double core, but it's not really a double core. Okay, so that's almost everything. What if you don't want to save? And this is the last thing I will show you. If you don't want to save something because you don't want to waste your storage space, so I'm going back to the system profiler command, but instead of putting it into a file, I just want to know something about my processor. So instead of using this thing, which is putting everything into a file, I will use the type, which is the vertical line. So this is not a capital I or an L. It is the vertical line, which is on the keyboard. Usually it's left from the enter key. So what it will do, it will give the standard output to a program, what I will write here. So I can use grep minus C processor here. So instead of grepping a file and looking into a file and try to find something in a file, I will grep the standard output of this program, the system profiler. So this will run first. Instead of putting everything on the screen, it will pass the standard output to grep, and grep will filter the output for me and only print the line if it has the processor word case insensitively in it. This is not coming out because of the grep. This is again the standard error, which comes out these 3 lines. So everything which is very weird. These 3 lines are standard errors, but these lines are from the standard output, which was filtered by the grep. Okay, I will stop here because it's already too much, but we will have a bit more and much more practice on Thursday in command line. If anyone has any problem having an own command line, I can open my Raspberry Pi and let in people, but I don't really want to open it for everyone because it's a small computer. I'm not sure it can handle 30 or 40 connections. But if you don't really want, if you are struggling installing a virtual machine, or if you don't have your Mac, then I can, or you don't have any other Linux servers you can work on, then I can open it for you. But you have to write me, or you have to ask me, and I will make it available. Okay, I think I will stop here now, and I'm very happy to answer any questions.
Thank you, Lajos.